Okay, now it's the time to move on to our last speaker of the day, of this session. Will be John Donovan. His talk will be on the topic of the light element analysis, quantitative light element analysis using EPMA. So John is the former director of the microanalytical facility at Center for Advanced Materials Characterization in Oregon at the University of Oregon since 2002. He's the president of Probe Software, a company that publishes software for electron probe microanalysis. He has been able to be an active contributor in the field of microanalysis for the last at least 36 years. He's also a non-traditional path to becoming an innovator and leader in the EPMA community. And he has begun this path with 26 years of technical service at the University of California at Berkeley. He has done many things, many contributions to the field, which are mainly centered to the methods which are able to improve the accuracy and precision of X-ray microanalysis measurements, including the spectral interferences, the big shape, shift characterization for light element, for the chemical state analysis, matrix corrections, and so many things. He was also awarded the MAS Makers Award in 1990 and the Presidential Science Award in 2010 for his software development efforts. He's also very actively engaged in raising public awareness regarding scientific issues and lectures on such topics. He has also a very nice YouTube channel with Probe Software where you can jump in, subscribe, and you can learn a lot of new things from the videos that are uploaded already there. So, John, thank you so much. It's a great honor to have you with us. You are expert on this topic, and we are waiting for your talk.
Thank you. Okay, I'm going to try to do a mixture of presentation and demonstration of software applications, and I hope it works. So basically, quantification of light elements basically includes all the things that we've talked about over this last couple of days and in the importance of all these things, but it has a few caveats that we need to consider. So this is mainly, we're thinking this is something like emission lines below 1 keV, for K lines, it's Z less than 11, and L and M lines for higher Z elements, which can also be very quite problematic. This may require layer dispersive element Bragg crystals, which in some cases might need to be optimized for each line. The composition of the layered multilayers is like, for instance, oxygen is usually tungsten and silicon. It's because those elements don't absorb oxygen over much. And for nitrogen or carbon or beryllium, boron especially, you might need crystals that are optimized just for that X-ray emission line. So it can get, you might need to configure the instrument for the specific applications that you're dealing with. There's also very large absorption effects for these things. The mass absorption coefficients, once you get into the 10 to the 4 range or higher, you're basically looking at a 1% accuracy effect in the MAC determination is a 1% change in your composition. This may mean that we might want to look at matrix match standards, but there's problems with that as well. So we'll deal with how can we correct this if we don't have a matrix match standard. Peak shape effects is one of the large problems that we have here. This means that we want to either acquire integrated intensities, just like we would for EDS, but with WDS, we would just scan across the peak and acquire that and integrate that intensity between the backgrounds. And that is very, very, very time consuming. Or we can use area peak factors a la Beston. And that is something I will talk about. Beam sensitivity effects, TDI effects can be very significant for some light elements, mostly because the absorption corrections are so large and any ion migration is going to affect the light element emission very strongly. And we have to also deal with interference corrections because as you go to lower and lower energies, the possibility of interference from higher Z elements becomes even greater. And this has been discussed previously in some of the other talks. And someone asked about coding corrections, differential absorption, and yes, we have to deal with that if we are using different codings on our standards and unknowns. So here's just a comparison between EDS and WDS, and why would we want to do light element analysis on EDS, on WDS, excuse me, rather than EDS, and it's because of the much higher spectral resolution of the WDS, and we're going to have the peaks are going to be more cleanly separated. We're still going to have to deal with some overlaps, but they're going to be smaller than compared with EDS. So that's the main point there. The matrix correction, as we all know, is and by the way, I should mention that this relationship, which is Castaing's first approximation, is a mistake. He should not have referenced it to mass concentration, but that's a story for another day. In any case, we have to deal with absorption, which is the blue curve here, and also fluorescence, which is the red curve here. This is a binary iron manganese in which there's almost no absorption or atomic number effects. And so you end up with almost a linear relationship between the concentration and the intensity, but that's not usually what happens. And in the case of, and this of course is the full correction here, and ZAF could mean any matrix correction. It could mean Phi-Rho-Z, could mean, anything, Monte Carlo, doesn't matter. But when we have a large absorption correction, that curve is very nonlinear. And so that is the main problem that we have to deal with. So what about standards? I showed this slide, but previously we have disagreement between even normal elements, iron, magnesium, aluminum, sodium. These are pretty straight, easy elements, and yet we have disagreement between the labs. And so if we're gonna, analyze oxygen, nitrogen, fluorine, carbon, whatever, the standards become even more important because of the absorption correction differences. So you can try to match standards. I've never found it to work that well, but it depends on the situation. Anyway, this is the paper here. So what oxygen standard do I use? I use magnesium oxide. Why? Okay. Well, it's something I will tell you about in a minute, but let's divert to Bragg diffraction. So this is a slide from John Fresnel, and he basically is looking at the equation for Bragg. And one of the things that is often overlooked is that we need to include this K. The K is the refractive index for the crystal material. And for normal crystal materials, LAF, PET, TAP, that refractive index is rather small, and it's not a large effect. But as we will see, the effects for the multi-layers, which are not made of light elements, sometimes they're often, because of we want to get a pseudo diffraction, we want to use a high Z material next to a low Z material. So the low Z material might be carbon or silicon or something like that, but the high Z material could be tungsten or whatever, and that can have a very high refractive index. So how do we deal with that? So let's take a quick look over here. And I just point out, this is the software packages that we mostly provide. The CalcSAP and Standard are free, and they are very useful for all kinds of modeling and what ifs. CalcSAP tends to be more looking at unknowns, Standard obviously looking more at standards. And this is our main software for point analyses and EDS and everything, and this CalcImage is for mapping. So let's take a look at CalcSAP because it's free, and it demonstrates this refractive index effect very nicely. So when you run CalcSAP, one of the many menus you can open under X-ray is calculate spectrometer position. And it turns out that you can put in here, say, iron, K alpha, and you'll notice that the K index, that's the refractive index here, is a pretty small number. And so when we calculate its position, and you'll see in the log window here where the ideal position for a Joule probe, where that line is going to show up on an LIF crystal, and you can choose different crystals, whatever you want. And if I say use the refractive index correction, and I calculate the position again, it's almost the same number. It's only different in about 100th of a millimeter. So it's not much of a difference here. But now let's look at a different element. Let's look at oxygen, for example. And let's turn off the refractive index correction first, and we'll change the crystal to like a PC1, or I guess LDE1 would be the same effect. But for me, I'm used to a PC1 because I'm used to Kamika. And you'll notice the refractive index now is a larger number. And we calculate its position here, we get 109. And then if I turn on the refractive index correction, I get 110. So it's almost a millimeter difference. Okay. So let's keep that in mind. And then we're going to go back here. And So here's the problem: is we have different orders of emission lines because Bragg diffraction. It's n. It's sine theta equals n lambda. So we need to look at higher energy lines that are showing up in the energy regime of our low energy lines due to Bragg diffraction of higher orders. And so this is a really nice plot that Julian Allah made, where he basically plotted up due to the refractive index where the third order phosphorus line appears relative to the phosphorus K alpha line, and they actually switch position. So if you don't do a refractive index correction, you're actually going to see the phosphorus third order line show up in the wrong place, completely on the wrong side of the peak even. And so what you need to really do is determine what your refractive indexes are for each of your crystals. I don't know what Ovonics, Osmic used to be called, is doing now, but my experience and John Fresnel's experience was when they tell you the 2D spacing of the crystal, they're measuring that by a cross section looking at an SEM, and they don't account for the refractive index effect. And so you need to include that, and that's something you can look up on the forum and things like that. There's explanations there about it. But John found, for example, on his 60 angstrom nominal 2D, he went from 61, which was the manufacturer reported result, to 62. So quite a large change there. So the peak shift effects are another of the problems that we can have, and this was already shown by Erie, I think, about sulfur K alpha in different minerals can actually show a quite significant shift. Fortunately, these shifts are pure shift. There's no change in the peak shape. And so as long as you repeak your spectrometer at the correct position, you will actually get a good analysis. But in the case of an element like oxygen, the peak may have a slight shift, but mostly it's a shape change. And these effects can be something on the order of 5 to 10%. So, and so why MgO? Well, it's because we know exactly what its composition is. There's no question about what its composition is. If we're using Kakanu hornblende, what is the composition of oxygen? Well, it depends on the ferric iron ferrous ratio. There's all kinds of issues with that. And do we know the chemistry that well or not? Is it homogeneous? All that stuff. But a synthetic high purity MgO is 1 atom of oxygen and 1 atom of magnesium. So we know the composition. And it's extremely beam stable. Periclase is an amazingly robust mineral. And it's inexpensive and high purity and easy to mount and polish. And also it serves as a nice fluorescent mineral for our beam location. All right. So the area peak factor correction that published by Beston back in the 90s is a very cute little equation. It's basically relating the integrated intensity to the peak intensity between the unknown and the standard, and coming up with this correction factor. Okay. And in the simplest case, here's an example of looking at fluorine K alpha and comparing calcium fluoride to barium fluoride. And the first thing you'll notice that even though calcium fluoride has a higher concentration of fluorine, almost more than double of the concentration in barium fluoride, the calcium fluoride peak is much smaller in intensity. Well, what's that because of? Well, here we can see in this mass absorption coefficient table here, we can see that the mass absorption coefficients for fluorine and barium are pretty reasonable. They're a little high, but not too bad. But the same fluorine K alpha in calcium is a very large mass absorption coefficient, huge absorption correction. So this needs to be noted too. And what it really means is that for some light elements, and I say for most of them, we really need to determine the mass absorption coefficients empirically. In my software, as I'll show you in a moment, we have a lot of empirical measurements of mass absorption coefficients as opposed to calculated values, which is what most tables are consisting of. And what we want to do instead is to actually do some measurements. You basically measure the intensity in a material. Usually a simple binary is ideal, because then you don't have to iterate so much. But you basically measure at a few beam energies. That's the red dots here. And then using the software such as XMAC by Pouchot, you can actually back out the mass absorption coefficient, as you can see down here. And you'll notice that the mass absorption coefficient for these different elements can be quite large. All right, so let's keep going. And here is a plot of looking at where I've plotted up the calcium fluoride here, and I plotted up the barium fluoride here, and I've done this, clicked on this integration button here, and it now gives me the integrated intensity, the peak intensity, peak intensity, integrated intensity, the peak over integrated ratio, which is what you're supposed to use for the standard, and then the integrated over the peak ratio, which is what you're supposed to use for unknown. And then you multiply them appropriately. And in this case, we get a correction factor of about 0.81 for this particular spectrometer. And it will be different for every spectrometer, by the way. So, you have to, make sure that you're being careful on your measurements. And when we apply this, and this is the EDS is the beige line or whatever that is, and then we apply the correction, the EDS and the WS overlap. Now, this is a very simple compound, obviously, but it makes a good point. So let's pull up Pro for EPMA, and let's look at some area pictures. I'll look at that barium calcium fluoride materials that we just, and I'm going to say, no, I don't want to connect to the instrument. By the way, if you click yes there, it will run in simulation mode, and you can do all kinds of neat simulations. It's all based on EPMA modeling for WS and EDS. So if I open up that run here, and the first thing I want to say, oh, it's William Röntgen's birthday today. Did you know that? All right. So we're going to go to this analytical analysis options here. And you'll notice I have the empirical MAC option checked and the empirical APF checked and this aggregate intensity checked. And you'll see why that is in a moment. I'm going to turn them all off because you can turn all these corrections off globally. And I'm going to first analyze the calcium fluoride, which is going to be not that interesting because it is the standard for the material. However, you'll notice we have some very large errors here. And it's because, of course, we actually are analyzing, let me open this window up a little bit more. We're actually analyzing fluorine on 3 spectrometers, okay? And I turned off the EDS just to make things simple for us, but that's another thing. So I'm going to go back to this analytical window here. So we're getting a total of 157. So that's a matrix correction will not work when you have duplicate elements of a major element. So we'll go back here and we'll turn on the aggregate intensity correction. And now we go back to analyze and click that button there. And now we get a good total because, of course, it's combined the intensities of all these spectrometers into one spectrometer. And it's the standard, so of course we get a good result. But now let's analyze our barium fluoride using that calcium fluoride as the primary standard. And we're getting 104 weight percent total. And in fact, we're off 20%. And what was that correction factor that we were seeing before, about 0.81? Interesting. So let's apply that correction factor. We're going to use a specified APF factor. I should probably show you that. But yeah, basically in the software, if you go here and you look down here, you can see the specified APF down here in the lower right corner. So it's in this particular spectrometer is 0.827. So, and there's a little bit of an averaging effect going on here, but now let's go ahead and analyze this. That's the raw counts there, combined from all 3 spectrometers. And now we get 100.25% total, and we're within 2% of our published value, the stoichiometric value for barium fluoride. So this does work. What do you know? So I'm going to close this off completely just so fewer windows open. And we're going to continue. And please post questions in the Q&A. I'll try to answer them later. And anyone who wants, any of the panelists who want to answer them, feel free. Okay, so APFs are measured. Compound APFs are different than specified APFs. A specified APF is we have a particular unknown, and we have a particular standard, and we measure the peak shapes in both, and we calculate a correction factor for that unknown using that standard. Now we're going to do something different. We're going to synthesize our APF factors. We're going to compound them based on the actual composition of the unknown, and which means it can be applied to different compositions as long as it's the same elements. So in this case, we're going to take the area peak factor for binary compounds where we have an element bonded to our light element. So that might mean we're using MgO as our standard again, but then we're going to look at oxygen in SiO2, oxygen in Al2O3, oxygen in whatever, iron oxide, whatever. And when we do, and I should mention that it's a little more complicated than just summing them up for reasons that are too long to explain right now, but that's the code. Okay, so now what we can do is we're going to take these, what we call binary and APFs from Baston, and some I've done myself, and we're going to compound them. We're going to put them together in a compound. Now, the good news is I use MgO as a primary oxygen standard, and Baston used Fe2O3, and just by sheer luck of the Irish, the correction for FeO to MgO is 1.000, as you can see here. This is from his original table, and for magnesium oxide, the correction is 1, because he was using Fe2O3 as a primary standard. Interestingly enough, for Fe3O4, it's a very, very slightly, could be experimental error, but he measured it. I think it's within variance, but that's what he came up with. So what do we do? So, and that's been published in the Green Book. And let's see. Yeah, so you need to measure these on your own instrument, because you might not get the same D-spacing. It depends on the age of the multi-layer. You'll notice in some of the work I'm going to show you that, like for instance, Baston came up with an SiO2 area peak factor of 1.04. I get about 1.07. So I've got a somewhat larger area peak factor. Why is that? Well, I think it's because he did this work in the 90s and the multi-layer technology wasn't as good. So what do I mean by good? To get a worse correction factor is that the new crystals are much smoother. The layers, the smoothness of the multi-layers between them is much smoother. So we actually have a higher resolution crystal, higher spectral resolution. But higher spectral resolution isn't everything. So by having higher spectral resolution, we're more sensitive to peak shift and peak shape effects. So it's a trade-off. In fact, with the old, I don't know if any of you remember, the old stearate crystals that we had, which were soap films basically deposited, those had even higher resolution, and the peak shape effects were even worse for those particular materials. But we don't use those anymore. So resolution can be a blessing and a curse. In my software, I have all these, the ones that are not referenced here are from Baston, and the ones where I've measured them are there. And this is the ones we've selected for our run. And let's see, yeah, so I'm using MgO as my primary standard. And the normalization factor is 1. If you're not using MgO as your primary standard, you can renormalize it to another standard. In this case, we've renormalized it to silicon oxide, and so we basically are dividing by the silicon oxide normalization factor. So now all these area peak factors are normalized to silicon oxide. So you can use any standard you want as long as you normalize it, and it's very easy to do in the software. And so here are some measurements I did where I looked at on each of my different measurements here. I did a bunch of measurements here and then averaged them together, and I got about 1.02 going to Al2O3 and about 1.07 going to SiO2. And you can see my aluminum oxide values are pretty close, a little bit larger, but my silicon was worse. And so I think that has to do mostly with the improved resolution of the modern crystals. Yep. Okay, so let's get back over to the software. And let's look at, I'm going to go to, yeah, let's do this one. Yeah, Röntgen again. And so if I, again, go to that analytical options window, I've already turned off all these options here, good. And now I'm going to first analyze MgO. I'm going to just look at my notes, make sure I don't forget anything. Oh, let me yeah, okay, good. So there's MgO. We're getting a good analysis of MgO. Of course we are, because it's our standard. And you can see here the percent variance is 0.01%. And it's in parentheses because it means it's the standard for itself. See here, we're analyzing 912, and the standard assigned is 912. So but if I go into the analytical menu here, I can do a couple things. One is I can go here to look at the empirical mass absorption coefficients, because these are measurements that Baston did and I did. And I'm going to use these mass absorption coefficients, and that was using those different voltage measurements where we can actually iterate back and extract out the mass absorption coefficient. So those are going to be turned on when I click OK here. And then if I go and look at the area peak, okay, let's just do the max first. And now, oh yeah, oh, sorry, I'm going to turn that off again because I wanted to show you one thing. Turn off the MAC, empirical MAC values. Let's analyze SiO2. Okay, we're getting about 94 weight percent. So let's now add in the empirical MAC correction and analyze again. And now we're getting 96, a little bit better, a little bit better. And now let's go and turn on the empirical compound APFs. You see, you can use a specified one, which is based on a fixed composition, or you can use a compound, which is based on binary compounds. And let's click analyze again. And now we get 99.3. So pretty darn good. And we're within 2% of our published value for SiO2. And I don't know if I have time. Yeah, I guess, I don't know. Yeah, okay, I'm going to do one more thing. And just to show you.
have plenty of time, actually. We are fine.
Okay, good. So let me go to here, which is, I'm now going to take a run, the same run, same data, but what I've done is I just made a copy of the database, and I'm going to turn on these guys again. Okay, well, here, I'll turn them off. And I'm going to go to the Analyze window, and here's SiO2 without the corrections, and it's close because now you notice again, I've changed the standard assignment to 914. So when I analyze the silicon oxide using itself, of course I get the right answer. But now let's go and extrapolate back to magnesium oxide. And you see I'm getting 104% total. Okay, I'm off 11%. Okay. So let's turn on both of those corrections just because we're going to save time. And we click analyze. And now we get 100.49% total. We're within 0.9% relative error. So that's good, right? Pretty cool. So let's close that. And all this data correction can be done offline after you've already acquired your data, assuming you acquired it appropriately. So now let's talk about interference corrections. This was all developed. So back in the 70s, Gilfrich proposed a method for correcting of interference corrections by doing a ratio of a standard between the unknown and the interference standard, which is this S bar here. And that's, of course, relative to the actual primary standard. And it worked okay. The problem is that if your unknown was quite different than your interference standard, and by definition, they have to be different because the interfered element cannot be present in the interference standard. So, and this is how we do it, is a double iteration. What we did, we said, okay, well, let's relate it to the concentration in the unknown and the concentration in the interference standard. And if we do that, then we can actually get a completely rigorous calculation, at least as rigorous as the ZF or phi rho Z calculation is. That was published in 1993. And here is the full expression, including this is just the correction term right here. This is the intensity of the unknown. And then we put that intensity in the unknown, right here. And then this term here is the correction factor for the interference correction, which is this guy right here. It's just straight math. And then if we do all this and we do everything right, we can now analyze oxygen with interference corrections or not in different materials, and we get a very good result. In this case, we're actually calculating the oxygen in the excess oxygen from ferric iron in an iron titanium oxide. So we can actually measure oxygen and get quantitative results if we just think about the mass absorption coefficients and think about these area peak factor corrections. That's all it takes. There are also TDI effects, and this is, of course, carbon, where this is going to be if I just take and do an analysis of carbon on my instrument, which, by the way, is a very clean instrument. It doesn't have, it's not turbo pumped, but it does have a 100-degree Kelvin chilled baffle right over the diffusion pump. So we don't get any backstreaming. And we're still getting, though, about maybe 1%, a little less, maybe 0.75% of carbon on the surface from the acquisition. And if we apply a TDI correction, you can now see that that carbon has actually essentially gone to zero, except for a few spots there where we accidentally spilled something on the sample, or maybe some spit, or who knows what. Anyway, that's with the TDI correction. So now let's go back to the software, and I'll show you some examples of this. Let's see. Oh, I can show you on a complicated. Let me show you on a complicated silicate here. So I'm going to check to see that going back a little bit. I'm going to go back here. This is what using MgO as my primary standard. But now I'm going to analyze diopside without the mass absorption coefficient. This is an old version of a data file, so it doesn't have prints out the specified and analyzed elements on different lines. So here now we have the analyzed and specified elements because we didn't measure magnesium, as you can see here. So it's a specified element. So we added that in because it is a standard, so we do know what it is. And here's and we just measure, actually we're specifying all the elements except for oxygen. Here's our oxygen measurement here. And we're off low by about 6%. We're getting about almost 7% relative error, and we're getting about 97% total. We turn on the corrections and we analyze diopside, and now we get 100.265% total. We're within 0.7%. This is an actual measurement, just measuring oxygen. You could, of course, analyze the other elements too, but I was lazy. But it does work amazingly well, actually. And then finally, let me open up this. Yeah, I want to show you the interference correction thing real quick. So measuring carbon in these are some commercial work we did. And if you look here, you can see that we were correcting for the interference of copper on carbon, copper on nitrogen, and nickel on nitrogen, and also manganese on iron, which we all know and love, and chromium on manganese, which we also know and love, because the beta line of every transition element interferes with the alpha line of the next transition element above it. That's true, by the way, both for the K and the L series. So anyway, if we analyze this guy, but first let's look at some. Let's see. Let's just look at the carbon here. And if I plot this up, oh, I don't think I did any TDI in the point analyses. No, I didn't. Okay, I did that only for the mapping. But let me instead just show you. I know what I'll do. I'm going to analyze. I'm going to turn off. Let me turn off the interference correction, which is right here. And then I'm going to analyze the copper standard. And we're getting about 0.67% carbon and about 0.36% nitrogen in the copper metal. That means that we can now correct for the interference because we now have a measurement of the elements being interfered with in a material that has the interfering element. So I now turn on the interference correction again, and we analyze again. And as you can see, we now have perfect correction here. Of course, it is the interference correction standard, but it doesn't matter what the material is, we're still going to get a good correction. And in fact, if we now analyze our unknown rotor, these are just some point analyses here. Since I changed the condition, it's going to reload the standards automatically. And you see we're getting average about 100% total. And we can see that the interference corrections is a small correction on the carbon, but a 0.39% correction on the nitrogen. So, this is now as correct as it can be. And so so you can do, and here we're getting up to 2% carbon here and 4% nitrogen, and we're getting a nice 100% total because everything's been corrected for. And if I have time, I'm going to show you a map. That was a traverse. Now let's do a map in our calc image software. So I'll load that project in. And here's the carbon and iron. And so here's our raw data. And by the way, this is using mean atomic number backgrounds. And you can see the setup of the analysis. We analyzed for carbon, iron, and nitrogen. And we used MAN backgrounds here. You can see we ran 200 milliseconds per pixel. If you're doing quantification, you want to run at least 100 milliseconds per pixel, maybe 200 or even 500, depending on the sensitivity you need. And calculate a totals image. We do atomic percent. We do output detection limits. So we're going to do some things here. And then I already calculated these. So rather than do the calculation, which takes about maybe 10 to 40 minutes, depending on the number of elements and the number of pixels, I'm going to just instead open the images for first the quant. Oh, let me show you one thing first. Sorry. If we go into the standard assignments, which is the same thing we saw before, we can now show you the TDI curves. So here are the TDI curves for carbon. So you see carbon increases over time, not surprisingly. And this is because we did multiple frame acquisitions. So we actually did a number of smaller acquisitions, and each of these dots here is a frame. And so we were able to extrapolate back to 0 time here. And this is over, almost half a day here. And we can do the same thing looking at nitrogen. I can't even remember what nitrogen does. And it's basically statistics. And that's looking at every 10/24th pixel, just because it'd be a lot of pixels otherwise. Okay. And now let's go ahead and look at the data. We'll open up the images for the quant. And now you can see we are getting essentially fully corrected for carbon here. And this is our iron. And this is the iron metal. And this is iron. And this is the total, sorry. So this is our total, measuring iron and measuring nitrogen and measuring carbon. And we're getting about, you see we're essentially oscillating around 0. If we want to see this more clearly, we can export this. We provide this software with our software. It basically, you can create a presentation quality output. And we can just run that. And it takes a pre-formed script, which you can edit to your heart's content, and it will now display those results here. So you can see the iron, you can see the total, and the nitrogen and the carbon. So, and then you can tweak this for your own presentations or papers or whatever like that. Ends up being very cute. Oh, and then there's a backscatter map as well. And you could display 4 maps per page, 9 maps per page, or 1 map per page, depending on how you want it to look. Let's see. I'm going to just do one more thing. I'm going to open up let me close these images here. Actually, I'll just do this. It's easier just to output it. I'm going to output the detection limits. So you see, because we're doing full quantification, we have the full statistics at hand, and now we can basically calculate the detection limits for each element. So for iron, we're getting about 0.3, that's a 3 sigma. Carbon is actually slightly, oops, sorry, it goes away automatically. But you can reopen it up and you can look at it again. But we can also do atomic percent. So whatever, you can do formulas, you can do oxides, and it'll log. You can do mineral end members, chemical age for monazite, and you can even do the TDI correction maps, or endomatrix correction maps even, including raw intensities, everything. So there's quite a lot here that you can enjoy. And oh, I didn't calculate the atomic. I just had checked that box, so it warns me that I need to recalculate that. So I can take some questions. In the meantime, I'm just going to rerun this in the background so that you can see how the quantification goes. I'm going to recalculate all these images just so you see the process. All right, there we go. So there you can see down here the pixel count. And if I open up the log window, we can see the results actually coming in real time here. It runs a little slower when it's got the log window open, but it is sometimes nice to see calculation going on in real time.
Okay, that's nice. Okay, so you have finished, I guess, so we can switch to the questions and the discussion session as well. So one question is, how is the aggregate intensity calculated? Is it an average of concentration from each spectrometer?
Okay, so great question. So the full answer is in the 2011 paper in American Mineralogist by Donovan et al. That was with Heather Lowers and I'm blanking on his name now, sorry. One of her students at USGS in Denver. But basically what you do is, so you do not want to normalize. If you normalize, you're going to ruin your statistical calculations. So what you want to do is you have two spectrometers. You want to basically imagine that you've taken those two spectrometers and those crystals and you've made them into a giant crystal that's twice as big. Okay, so all you're really doing is increasing the geometric efficiency. And so as we all know from EDS, the larger the EDS detector, the better sensitivity we get, right? So we can do the same thing with WDS. We basically analyze the same element on two spectrometers or 3 or 4 or 5. And when we combine them, we take the counts from one spectrometer and the counts from the other spectrometer for the on peak, and we add them together. And we do that for the off peak, the low off peak and the high off peak. Basically, we do it for every type of data that we acquire, including TDI, by the way. And so the code is a little complicated, but basically we basically compile all the intensities from each of the data types together from each spectrometer for the unknown and the standard. And that's the critical point that people miss, is that you need to do this for the standard as well as the unknown. And then, of course, then the matrix correction is fine. Now, if you're doing just trace elements, it wouldn't really matter if you had 4 spectrometers and you're getting 100 ppm in each spectrometer. As I pointed out in my talk yesterday, the matrix correction is a very minor effect at the trace level. So as long as the matrix is SiO2, it really doesn't matter if you measure titanium on 1, 2, 3, 4, 5 spectrometers, but you will improve sensitivity when you aggregate them also. So you can get the titanium from each spectrometer, and that's useful, and make sure you do the blank correction, because each spectrometer will have a different blank correction, and it depends on the orientation of the PET crystal actually to get that secondary Bragg diffraction that causes those little negative holes in the continuum. But when you aggregate them after you've done the blank correction, then you now are getting like a giant spectrometer, and that giant spectrometer now has much better sensitivity, and basically each doubling of the counts improves the detection limit by the square root of 2, as we know. And so and that's why we were able to demonstrate, we were at, I think, 100 or 200 nanoamps and counting for 200 or 300 seconds. But we were getting a t-test, 99% confidence of 2 to 3 parts per million of titanium and quartz. Now, other elements won't maybe be as good. Titanium is a very nice, robust energy emission, not too much absorption. And quartz is relatively beam stable if you defocus the beam a little bit. And so there's no problem there. Now, other situations, like if you're analyzing for trace oxygen in vanadium, good luck. It's a bear. So it depends on the physics of the situation. But you can get improved detection limits by using multiple spectrometers. That's all I'm saying.
I have a question before we move to another one from one of our attendees. Now, we are actually aware that it's really difficult to measure rare earth elements by EPMA technique, rare earth elements. So using a software like probe software, is it easier to evaluate or to have a better accuracy of rare earth elements,
What do you
especially
think I'm going to say,
because of the
Analyst?
interferences?
What do you think I'm going to say? The answer is yes.
Yeah, but
and the answer is yes
we
for
need a
very
longer answer actually to more justify.
I know. I'm joking, but the answer is a very specific reason. And the reason is that, so I basically about 10 years ago now, I worked for a long time with Mike Trasinovic at University of Massachusetts and Julian Allah, who was a postdoc there at the time. Now Julian's at ETH Zurich.
Mhm.
And we developed a method called multi-point background. And the reason for this is that if you pick 2 points to measure your backgrounds on, it might work. And if you do careful wave scans and you pick your backgrounds very carefully, it might work in one material, but it might not work in a different composition, even a different monazite composition, because what they had was problems with elements that would just happen to be in that little area of the crystal, whether it's sulfur or some other element, and it would interfere with the background position of one of those 2-point backgrounds. And it's a sloping background. So you do need 2 points to measure the background slope. And also, some of those backgrounds are curved. Okay. But if you, instead of measuring just 2 background positions, you can measure 3 or 4. And I wonder if I have an example of this. I think I might have an example of this. Let me see if I can find an example of this. I mean, I'm not the monazite person. Mike and Julian and other people are much better at this than I am, but I think I did a test run a while back. And by the way, when you open in offline processing mode, you can open data files from Kamika instruments and data files from Joel instruments. It doesn't matter. So this may be, let me sort alphabetically and see if I can find monazite here.
I would also just while you are just searching your files, also to include also Sergey into this discussion, because okay, we are a workshop, we need to learn from this, and the question is, can you follow or something like a similar process by applying this routine by
I don't
from
think so, because I'll tell
Geos
you,
or Kamika software, or
no, the answer is no, and it's because it's the acquisition process that has to be different. So on a Joel or Kamika probe, you acquire your on point, your peak position intensity, and you go off peak, and then you maybe go another off peak. But
okay.
here you go on peak, and then you go off peak, off peak, off peak, off peak, off peak, off peak. You're doing multiple backgrounds, and in fact, okay, so here's a good example. So here I'm analyzing. What am I analyzing for? Let's just look at the raw data.
You have to share your screen.
I'm sharing it. You don't see it?
No. Sorry.
Okay.
I will put
I'm seeing
mine.
it. I'm seeing
Oh,
it.
oh, you're
I thought
seeing
it was
it?
okay.
Okay.
Yeah.
I'll reshare.
Yeah, okay.
Okay, so here, do
Yeah,
you see
yeah.
this? Okay.
Yep.
Yep.
So here we're running at 150 nanoamps, and you'll notice that well, in this one, these are unfortunately all off-peak measurements. Okay, so this file doesn't have the multi-point background. Let me see if I can find another one. The easiest thing, actually, you know what? I'm going to just do this. So rather than search for a file, I'm just going to go to the user forum, and I'm going to type in, and this is how you do it. You go user forum. You can go to a specific topic like probe for EPMA, and you can go multi-point and click search. And here's a multi-point background question. Here's multi-point background file setups, short guide to the multi-point background. Let's start with that. Let's see. I'm thinking that, and there's people who are posting questions. And okay. So this is Julian Law. So I'm gonna just log in here, and I can click now on, if you log into the forum as a member, you can see attachments, and here's the multi-point background acquisition PDF. And here he's basically showing what you do here. So basically, you select multi-point as your background type. So we can do normal off peaks, we can do MAN, or we can do multi-point background types. And then in this window here, and the software has changed quite a bit since this was written, it's gotten much better. You can tell it how many points you want to acquire off peak. So here's 4 on the high side, and here's 4 on the low side. And then you can say you want to iterate to 2 points only on each side, which means we acquire 4 off peaks on each side, and then the software fits all those 8 background positions, and then it looks at the variance, and it looks at what the high outliers are, because that would mean an interference with the off-peak position. And then it throws those away, and then it recalculates the background. And it does that iteratively. And when you're done, and this is very old graphics here, but when you're done, these are the background positions here, and then it will calculate the fit, and you can determine how many you want to iterate to. And so this is kind of a whole explanation of that. And I was hoping there would be some better, let me go back to, let's see, background. And then here's another option, which is pretty wild, is you can acquire normal off peaks on each of your elements on a spectrometer. And if you're doing more than one element on a spectrometer, you can share those backgrounds with the other elements. So here's an example, and the red circles are where we've actually are using the fit. And there's some code there. And anyway, there's lots of examples here. This is an idea that's suggested by Carsten Goman at the University of Tasmania. Yeah, here's an example. Here's some images that Mike Jasinovic posted. He's showing the problems of the background shape. Here's that argon absorption edge, that we all know about in the argon detectors. And here's an example of where he selected different backgrounds and how it uses them. I'm trying to find a better example. This is my old graphics. We have much prettier graphics now. In a while, maybe. All right. Well, I don't want to use it too much time, but basically, yeah, you can actually use multiple backgrounds with either. So here's an example of some backgrounds where these two were interfered with by something, and so then or were too close to the peak, and this one was an outlier here, and we selected just to use these, and so you can get a curved fit on a sloping curved background.
So in any case, you select manually the background. You're going.
Well, usually what you do is just like what you do for a normal wave scan for off peaks. You acquire a wave scan, and you can click where you want the high background. You can click where you want the low background, right? But when the multi-point backgrounds is you click in multiple places where you want each background. So it's exactly the same selection process. Okay. I mean, it's slightly different because of the number of backgrounds. Yeah, so in fact, I was hoping to see a cute picture where you can overlay a wave scan on this data, and you can see how it actually looks in real time, but unfortunately, I am not seeing it in this particular topic. Give me one more chance here. So here's the new graphics, and you can see someone's asking questions about this. I was hoping that there was going to be don't know why I can't find it. Yeah, I don't want to search for it now, but there's some nice examples in the forum. Let me try this. Hoping for some pretty pictures. All right, well, that's okay. Anyway, it does work, and it allows enormous flexibility. I mean, so I'll tell you. So I had a thin film analysis I needed to do, and I needed to start it Friday afternoon. And normally you want to do a wave scan and then pick your backgrounds, right? Well, I didn't have time for that, so I just switched everything to multi-point background because it's just a quick click with the mouse. And I ran it over the weekend, all these thin films, When I got back on Monday, I looked to see how my backgrounds were chosen. Well, yeah, I had made some mistakes. I hadn't selected backgrounds carefully, but the multi-point background automatically took care of it, and it automatically excluded the points that were interfered with. So it's pretty powerful. Yeah.
Okay. So another question is, can you set also probe image to acquire qualitative WDS maps, so only intensities? So that is quicker to have a full thin section map acquisition, of course.
You can just acquire maps and not quantify them. Sure, of course. I mean, the quantification is an extra step. Basically, what it is you can acquire raw maps, but if you have standards in ProPrePMA, which you're going to do anyway, right? well, now you can quantify any maps you acquire. It doesn't take any more work. It doesn't take any more acquisition time to acquire standards if you're going to do quant analysis for points, right? You can use this, you use the same standardization you use for your unknown points as you do for your unknown maps. It's exactly the same process. We treat every pixel just like a analysis point, a point analysis.
All right. I guess there's no other question from the audience. I don't know if Annette or Sergey or Ariadne, because they are still here, want to add anything to the discussion.
Yeah, feel free, anyone, to jump in.
Or to this topic.
I'm going to do another search here.
Yeah, there's another quantitative spectral interferences correction. That was one of the topics there.
What was that?
Quantitative was in the previous page.
And by the way, here's
But
a
the
topic
interferences.
here. Here's a topic here in ProFreePM called which background acquisition analysis method is best. And I mentioned that, you know, we can have the choice between off-peak, MAN, and multi-point. There's a discussion here of each of the methods here. Oh, here's the paper that we published. Yeah. And the cool thing about it is you gain precision because you're making more background measurements, and you're on, you know, because remember, trace elements, you're measuring intensities that are close to the background, right? So the more backgrounds you measure, the more precise it is. But also in the case of curved backgrounds, you have more precision as well. And so, you know, I probably don't have access on this computer for this PDF. But anyway, this is the paper that you should read, and this kind of goes into it in a lot of detail.
So
And,
this method can be even applied by from even an old GEOL or Kamika instrument. That it's not necessary to have a field emission or a new instrument. I mean, you need to have the software. Huh? Just to clarify that.
This method will work with ProFreePM on a Joel 8900, we don't support the Kamiga SX50, 51 anymore, but you know the Joel 8900, 8200, 8500, 8230, 8530, and the Kamiga SX100s are all supported.
SX5
and SX5.
Yeah,
they're all supported by ProFreePM, and that's kind of the thing. Like people sometimes, you know, like I think sometimes Kamika and Joel would wish I would just do data reprocessing on their data that they acquire. And that would make my life so much easier. It would make my life so much easier. But the problem is that the data needs to be acquired in a certain way, whether it's you're doing multi-point backgrounds, whether you're doing TDI, whether you're doing interference corrections, all these multi-point backgrounds, you've got to acquire the data in a certain way. And if you don't acquire the data in a certain way, then you can't reprocess it. And Kamika and Joel don't acquire the data in the ways that we need to do these advanced methods. So fortunately, Joel is very happy. I'll just show you something that I just saw today. We go to I can't remember who pointed this out to me. It might have been Sergey. But if you go to the most recent post, by the way, down here, this link right here, this is the most recent post on the forum. And this is the most recent post on the forum. If you go here, you'll get a list of the most recent posts. And I just noticed this today. This is the Joel website.
Okay.
And this is their IHP 200F instrument, which is a fantastic instrument, if I do say so. And one of the points they list is integration with ProFreePM. So Joel,
what does it really mean? Integration with ProFreePM?
Yeah.
In reality, I mean, what does it really mean? This integration?
Oh, it means that when you buy a new Joel probe, or if you have an old Joel probe, you get the Joel software, right, that talks to the instrument and does all the Joel things, and then you get a separate PC that runs ProFreePM, and they both talk to the instrument at the same time. And it's kind of cute. And Annette has this set up on her instrument. Some of the other attendees, I'm sure, do too. And basically it's kind of cute because you can tell the Joel software, move this spectrometer over here, or move the stage over here. And then if you go to the PFE software quickly enough, you can say, oh, no, move over there. And the stage will start moving and it will slow down and then change direction, going the other way. So you can actually, but they don't interfere with each other. They work together just fine. And don't forget, this is only possible. We couldn't do this with the SX100 and SX51 or the Joel 733 probe, the very old probes, because they weren't networked. But with a network connection to the instrument, you can have multiple computers talking to the instrument at the same time. And so this was a big deal for us because, in the past, we had to take, like on an SX50, you had to take the Kamika software off the connection off the instrument, and then you had to plug in the cables to the PFE PC, so people didn't get the OEM software. Now, when you buy the Joel probe, you get the Joel software, you get the Joel probe, and then you can buy the PFE software either through us or from Joel, and then you have best of both worlds, as I like to put it.
Yeah, and I would just add, yeah, they play nicely together with each other. When I arrived in the US to run a microprobe lab, it was an old 8900, and thankfully they had the probe software. And I mean, the JOL software is working well. Same with the Kamika. Inherently, it's just that certain aspects, certain things you can't really do. And I did a lot of light element projects on the old 8900. Again, the hardware is great. The newer generations have often more high intensity crystals and all that, but it's really the software side, having better background models, having access to more modern matrix corrections that really unlock this push then with old hardware when it comes to applications. And I mean, I also want to say I really understand why vendor software often doesn't necessarily include all these things. Academia is an awful client because we constantly want to push things, and they're like two labs that want to have that functionality that in the grand scheme of things, like from a profit perspective, doesn't necessarily sense to implement. And then of course we always want to have things now. We want to do a project this month and can't wait for a 2-year upgrade. And again, I'm sure I come across always as a total fangirl, but I really appreciate that John is so open to requests, and if he can, tries to implement it fast, and if he can't, he explains why not. But the answer is never because it's like, oh no, I don't want to do it. It's usually there's a very practical thing. And I was amazed also in terms of like old hardware. I know that there's an ARL just every day running in South Carolina. Was the coolest thing that I've seen because it just predates a little bit my experiences. And they're running it with an older version of probe software and do man backgrounds because they have 4 fixed spectrometers. Man backgrounds are really an old technique in a way that we rediscover. And so at times we can do really awesome things, even with older instruments. But yeah, it helps to have a software that records all the nitty-gritty details so that I can look at it again. Also, I really like it as a lab manager because they're like all these intensities that I can look at drift in the machine or something over years back, just with a small utility that harvests that instead of like, I don't know, having to type it out all the time. So there's also some aspects when it comes to quality control that are kind of nice.
We as a default save all the parameters. We save all the PHA scans. We save all the peaking scans. Everything's saved to one file. And so the best thing from my point of view as a lab manager is that the student can acquire the data overnight or all day or whatever, and I can give them their data file for that run, and then they can go to an offline computer and they can reprocess the data to their heart's content. And so that kind of frees up the instrument right away. And now I can get the next customer on the instrument. So those are kind of good things from a lab manager perspective. I think from Joel's perspective, and maybe Sergey can speak to that, but I think the main advantage from Joel's perspective is that they don't really want to do specials. I mean, they've done a lot of things in their software, but they don't want to do all these esoteric, weird, one-off kind of specials. And so their response now to people who ask for these weird things is say, talk to Donovan, you know, and that makes that makes everybody happy. And as the Joel Japan people told me, they just want happy customers. That's really what they want, is happy customers. So.
And to plug and going back a little bit to the presentation by Erie this morning, like even if you don't have this software, they're all.
Whoops, we losing it.
We lost.
I found incredibly powerful is just to be able to see like how much does it matter. Like there's often this kind of like, oh, I'm getting bad data and it's because of the metrics corrections or something else, and I can test that. I can check that even if I not necessarily have the software to apply certain things or to correct certain things, but I can use the modeling to see like, oh, can I get away with like not going. Yesterday we had well, 2 days ago we had like questions where people ask about interference corrections where the interfering element only is present at 0.1 weight%. I don't worry about that, specifically not if the interfered element is a major element, but the devil is in the detail. Sometimes it does matter, and again, there are these free, easily accessible modeling utilities. There are more and more tutorials in these kind of workshops, but also on YouTube and otherwise. And there's really kind of no excuse to not occasionally take, like if you run into a problem or beforehand, instead of saying like, oh, well, I don't have that, so this is what I will publish. There is the option to do this extra step to like, I checked it and it doesn't matter, or I checked it and it does matter, and now I have to deal with that.
Well, that's the benefit of, for instance, the modeling. We looked at a lot of modeling these last couple of days, and so when you can go into the standard application and calculate using PNETMA a secondary fluorescence profile, and you can immediately see, you know, I think we're running out of time, but I'm happy to show anybody who's interested. So respond on the chat if you're interested. But I can show you how we can put in different elements, different phases, and we can model to see, okay, if I'm analyzing this material near this material, I'm analyzing for this element, is that a problem? Is there a secondary fluorescence problem? And I think I've told this story before, but you know, I was contacted one time by a national lab, and they were analyzing zinc in a magnesium aluminum alloy, and they were getting these weird results, they said. And when they told me the particulars, I went, oh, I think I know what the problem is. And they were detecting zinc in a magnesium aluminum alloy from 0.5 millimeter away, 500 microns away. And, you know, it's because the zinc K alpha is a very penetrating X-ray, and magnesium aluminum is a relatively low Z non-absorbing material. And so 500, you think you were safe, right? You think, oh, I'm 50 microns away. I'm 100 microns away from boundary. Not a problem. But if you're measuring a trace element or minor element and you're close to that boundary, you know, even in this case, within 0.5 millimeter, you were going to detect that element, and it was a spurious artifact. And the worst thing was when I went to a geology talk one time, and it was at AGU, and I saw all these students putting up these different talks, and they were showing these diffusion profiles. Every single one of them was a fluorescence artifact. And that's when we wrote that paper that Erie cited, which was the Borisova paper, because I went to Paul Asimov and I said, Paul, I need to show you something. And he said, oh, wow. And he said, I'd heard of this, but I didn't know it was that big a problem. Well, it's not a big problem sometimes, but it can be a really big problem sometimes. And so they're trying to derive thermodynamics looking at fluorescence artifacts. It doesn't work. And the worst case was a student, shall go unnamed, who was publishing a paper, and I got it for review. And the student had assumed that all these profiles, and it was lunar material, so it wasn't exactly a simple, you know, straightforward analysis. They were lunar materials, and they were looking at these minerals and drawing conclusions about the thermal history of the moon, and it was all fluorescence artifacts. And what he had to do, and actually they had already submitted, they already had the paper had already been accepted, but he started to give a talk about it, and one of our colleagues took them aside and said, "You need to talk to John." And so the guy, to his credit, called me. And so what they had to do was in the last tweaks to the paper, they had to insert a little disclaimer every time they talked about fluorescence. Well, if this is not a fluorescence artifact, and of course they all were fluorescence artifacts.
We have a question from Charlene. Actually, we'll take the final question and then we should wrap up because we are already off. Related with John's talk from yesterday, do you change at all the PHA conditions during standardization, for instance, or do you use the standard one set by default during the maintenance?
Oh my God! Do not use any factory settings. The factory settings are just there to get you going. They're great starting place. Yeah, right. Sergey is there. He's there.
So he agrees.
Factory settings are there, but then you've got to
totally
yourself.
Yeah.
It was actually in Dual software. There is this function. I suspect that because in so the factory is, of course, designing instruments also for internal market. Internal market is largely industrial people. They don't want to worry about this PHA settings, so engineers will do it for them. In many places, like in Europe, or I assume in the United States or Canada, people just don't do this type of things. We don't tune. We assume that the operator knows how to do it. But what the danger is that there's this function. You can actually in Geo software, you can choose between both. You can use default values, or you can use tuned PHA values.
And the default values may be useful in
they
certain
usually not. From our market,
really not. Yeah, I mean,
we can do it. We can tune it and make it work. Actually, for something like steel industry,
it's going to depend on the beam current. It's going to depend on the count rate.
Absolutely.
Due to pulse height depression. So the higher the count rate, the more the PHA pulse is depressed.
Yeah.
And if that PHA, and that's the main problem with using tight baseline and differential window settings, is if you have that tight around the PHA peak, if that peak shifts at all, you're going to get cut off. You're going to cut off the intensities on the tails of your peak, and you get nonlinear response of the detector, which means that you try to analyze one composition, it might work. But you analyze a different composition with a different concentration, that is count rate, you'll get a completely wrong quantification. So you want to make your detector respond linearly, and that to me means you open up the baseline and window. In fact, I don't even use the window now, except in very, very rare situations. For instance, an interference of sodium on oxygen K alpha or something like that, where you kind of you tell me, is there a good sodium standard that doesn't contain oxygen? I mean, salt, that's not a great standard.
No.
So anyway, except in those very rare cases where I would use differential mode, I use integral mode only, and I open up everything as wide as I possibly can. Let that peak shift around based on count rate or concentration. And by the way, always measure your PHAs on the highest concentration standard that you'll be seeing that session, and at the beam current you're actually going to be measuring it at, because you want to look at the highest count rate, because when that pulse gets depressed, you want to make sure that baseline, which you always have to have there, make sure that baseline is not cutting off any of the left side of the peak. Yeah. So don't use the factory settings.
So
I assume that it can only happen. This is when I would say that yes, maybe. If I know that this lab is entirely industrial kind of environment, they analyze the same, they analyze quality of some sort of alloy, and it's over and over the same conditions, the same current voltage standards. So yeah, in this case, probably. But then I would tune it anyways. I would find somebody who knows what's going on and would tune it, because anything that comes, when I see anything, actually, luckily in Geo software, we have default values that are very recognizable. So for instance, PHA, like high voltage or baseline, it's all very recognizable. I can say, oh, okay, this value is, this background is 5 millimeters. This is in Geo terms this is default value, please change it. Always change it, because otherwise, if I see anything that is default, it means that the instrument is not tuned for the specific analysis. And in our environment, particularly in academic environment, it's you have to know.
I never know what's going to come in my lab, because I'm in a centralized service center, and so we get geology, anthropology, material science, industry. So you always, every day it's something different. So you've got to adjust for that situation. What am I trying to optimize for? That's a really important thing to think about, is not just where all the errors are, but how do I get the best measurement? You know, maybe I don't want to run at 15 kilovolts. Maybe I'm doing a trace element analysis. I don't care about spatial resolution so much. So I want to run at 20, 25, 30 kilovolts. Okay. Get more atoms involved in the interaction volume. Maybe I want to, you know, improve, you know, I want to get a very sensitive measurement for light element. Okay. Well, then I want to lower my energy, go down to like 10 kilovolts, 8 kilovolts, you know, because you're going to get much more efficient ionization at the low overvoltage.
So John said industry. That's a really good bridge with tomorrow's talk by Sergey, where he will talk about the application of SXES, soft X-ray related with lithium, and will apply this knowledge to the batteries industry. So this is very interesting.
But
Actually, with this XCS,
yeah.
with this XCS, it's interesting. We never actually work with voltages above 5 kV. That's our voltage. That's how it works best.
Yeah. So let's wrap up. Actually, thank you very much, everyone.
Ioannis, can you leave the Q&A open for a little bit longer?
Yeah. Actually, we'll have finished for today. Thank you so much again. But I will give you some time to type the answers for the 2 questions, and we'll see you again tomorrow.